Okay, so I'm going to record the video now. Okay. So we were studying about the first chapter, right? A tour to computer system. And it's the first chapter from the book. But this presentation has some things extra apart from the book as well, which I think is required because this book does not cover everything. Okay. So sometimes we feel that the book is not enough. Okay, so we had seen how your CPU works, right? Last class, we saw that this is a CPU which is attached to the motherboard and it has all these circuits. And there is a clock in the CPU. Then you have a clock speed with which you can say that your CPU can process fast. Like if your clock speed is faster, then you can say, yes, my CPU is fast, which means how many instructions it can process in given a second. So we learned about that. And then we learned internally how CPU actually looks and does things. So CPU has all these buses attached to it. So it takes just an address bus and data bus and the control bus attached to the RAM socket. This is your RAM, and you put that RAM in here. And there is an address bus which will give the address on which address in this RAM you have to get the data from. So that information goes from address bus, and then whatever data is there in that location, everything is 0 and 1. So you have to remember that. So whatever data is there in that location, those wires will be on here. So you will get that data in the data bus. Okay, so that's how CPU gets the data from the RAM. And based on what your computer capacity is it a 64-bit word or like a 64-bit words? Also, you can say 8-byte word or 16-bit or 8-bit. So modern computers are mostly 64-bit. Based on that, you can get that much data in one time, okay, from the RAM. So that's what it is. And in the RAM, you are this is a random access memory, right? So in here, okay, there are some more students. Let me add them. Okay, admit all. Okay, so in the random access memory, you have whatever applications you are running on a computer. For example, you are running this Zoom application or you are running a PDF file. Those applications are there in the hard drive, okay, in the hard disk, and you just when the computer starts and when you open the application, when that instruction goes, it will bring all the application data on the RAM. Okay, on the RAM. So it will have all the code, like the executable file on the RAM, and it will have all the instructions related to that particular application, and those instructions can be then executed. Okay, so I showed you with a very simple example. For this your C program, let's say you generate an exe, and exe will give you this kind of instruction set. So all the compiler job is to convert this high level language into a low level language like this. Okay, low level language is basically assembly language, and basically each instruction mapped to a 0 and 1 set. Okay, so this instruction that is loaded on the RAM. So RAM has all these instructions. So when you run this program, then each instruction is sent to the CPU, and CPU will perform based on what instruction is given. So for each of these instructions, CPU has the logic gates, okay, made with AND or NOR gate and a lot of registers. So they store the temporary data related to each operation, and then take those temporary data, do the operation for everything. For all these instructions, the design is implemented in the chip. So in this CPU chip. So nowadays the chip size is so small, you know that you cannot see these circuits with the bare eye. So you can see that circuit only with the microscope, because the chips, because the transistors in today's modern computers are very, very small, just 10 times bigger than an atom, you can say like that. Okay, so Samsung has made a transistor which is just 10 times bigger than an atom. That small transistor Samsung has made. So, but if the problem with the transistor is that it cannot go beyond that size. So that is the smallest possible size for the transistor. So now what you are seeing, the device size is, now it is impossible to make something smaller than that. So now the CPU size is like this much, let's say, and now it is almost impossible, like near to impossible, to make anything smaller than that. Okay, so before a long time ago, our computers were very big. It was the size of this room, for example, and now the sizes have come down to small computer like that on one chip, the entire computer on one chip, but smaller than that is impossible at this point. So there are other kind of design techniques that are now people are trying to accept for designing a better CPU. So with the silicon, this is I think we have maxed out the capacity of reducing the sizes of the transistors, and that's why, because we cannot reduce the size of the transistors anymore, it is hard to make a chip smaller than that. Okay, so that thing also is important, and to know. Okay, so this is how your, so inside the CPU, this is a very simple diagram of a basic CPU. This is a squad CPU. You can also go to the website and read more about the CPU, but this course is not only focused on the CPU designing, so we are only going to see the brief of this. So in the CPU, you have control and the arithmetic and logic units and all these registers, as I told you, and this is a data bus, and you have a address bus, and for the RAM data bus, and this is instruction set. So enable and set, enable and set. So each register will have those kind of instruction set. And yes, last class I explained to you how the instructions are taken from the RAM and stored in this register, special register, which is called instruction register. Now this address register, instruction address register, is enabled when there is a jump or something. Okay, so in your code there is a jump to this instruction, then that instruction will go here and it will enable this wire, so it will go travel in the bus and go in the memory address. But usually the instructions are executed in the sequence. Okay, but if there is a jump instruction, it will also be stored and passed to the memory. Okay, so the instruction then are stored here, and that instruction is executed by the control unit. So I'm not going in detail of how the logic gates are made inside the control unit. Those things you can study in the digital design course or some other computer architecture course. So this is an overall idea for you. Okay, so how this works. So for playing, for example, this Zoom application that you are playing, your CPU is probably executing millions of instructions per second. So this task is happening like millions times per second. That's fast. That's how fast our CPUs are in today's time. And as you can see that this is connected to RAM for the address and for the data and for the set and enable wire. And then you also are connected, this CPU is also connected to the input output device. So this side is, you can say, input output wires. So these are input output wires connected to your input output device. So when your program needs to print something on the screen or take some data input from the wires, so control unit knows which wires to enable and get those information from. So this is not very detailed design of input output, how it works, but you got the idea, right? How the input output is also connected to the central processing unit. Okay, so sometimes some processor were having like separate processor for processing the input output and passing it to the central unit. So that kind of, so several designs are possible for making this central processing unit. Okay, so this is not the only design. Okay, this is not the only, this is a Scott CPU design only, which very simple design, which I wanted to explain to you with. So this is, there are so many other designs for the CPU. So when you close this, now when you make this small, You can see this was your CPU and how it is connected to all the input output devices and the RAM. Okay, and on this jack you can put the RAM, and your data can be taken from the RAM and operated on the RAM. So random access memory, as you can see, its name is random access, means you can access any address. Plus it is a volatile memory. When you switch off your computer, this whatever you stored in this RAM will go. Okay, it will not remain on the computer. So everything you have to save it on the hard disk. So sometimes you have this experience, right, that you are working on some presentation and you did not save it. You're still working on it and something happened to the computer crashed or electricity went off or something happened, and then you lost whatever you had made because you had not saved it. So nowadays modern computer also keep automatic saving, save the state of your program, automatically saving it on the hard disk. But if that feature is not there in your operating system, then you lose whatever you are coding or doing. Why? Because the RAM does not store that data on the hard disk. So you have to save to store that data on the hard disk. Or if your operating system supports, it will keep storing it by itself. Like that kind of feature can be there. But the point is that RAM is a volatile memory, which means it can vanish. Okay, so it is not for persistent memory, so it will not store whatever you're doing forever. So every time you switch on the computer, your RAM is refreshed with the new application. As soon as you open the application, that application is loaded in your RAM. Okay, so that is random access memory. There is other kind of memories as well. So we saw a few memories here right now, random access memory, and you saw the registers, right? Registers are the smallest unit of the memory which are there inside the CPU. Registers are inside the CPU for storing the temporary data, right? So registers are also important concept. Okay, you have to remember what the registers do. Okay, so I hope that I have given you the idea what does the registers do, right? So registers are the smallest unit of the data, but then there is a cache. Cache are of three types. We will learn about them. So there are several memory hierarchy in your computer, not only registers and the RAM. There are also other memory hierarchy which are called cache, and then ultimately is the hard disk. So there are different levels of the memory. So registers being the smallest unit, and RAM, you can say third unit. Between registers and RAM, there are caches as well. And then there is another memory, ROM, read-only memory. Read-only memory is related to the hardware. So for example, you have to, you need computer to remember certain things like all the time. Okay, so random access memory, as you know, that it is volatile, but read-only memory are something that are on which your hardwares work. Like some information for your hardware is must to be there all the time. So for example, to boot your computer, you need some information, right? So bootable information. So for booting the computer, you need these kind of things. So those data are stored in ROM. Okay, like your BIOS data are stored in ROM. So there is another memory as well, which is called read-only memory, ROM. And nowadays they can also do a programmable ROM. So PROM is there. So before, long time ago, the ROMs were, you could not touch the ROMs, you cannot modify anything on the ROM. But these days you can also do some modification on the ROM. So when your computer boots, at that time you want to change something, you can also do those things on the ROM, read-only memory. But still, it is still called ROM only. Okay, so that memory is not here. I just wanted to give you that idea of ROM, RAM, caches, and hard disk plus register. So these are different kind of memories also will be there on your motherboard. Okay, so it's not only these things, there will be more things here. Okay, so that's your motherboard. It will be in your computer, and as you can see, it is connected to the hard disk. So one of the input output device is the hard disk. Okay, so all when you switch on the computer, applications are actually in here, which are loaded in the RAM. Okay, so through this hard disk. So hard disks are very, very slow as compared to the RAM. So RAM, you can see that they are connected with these buses directly. Okay, so fetching data from the RAM is faster, okay, compared to the hard disk. Hard disk is a magnetic disk. It will this jack will keep moving fast and fast and then access you the data, but it's still very slow. Okay, so accessing data from the hard disk are slower than accessing from this RAM. And then there is a among these input output, there is also a network interface card, an IC, which is connected. Through this, your data can transfer from this computer, and there is this port. Using this port, it can transfer from this computer to other computers or to the Ethernet wire to the cloud. So you can, that is another full course for the networking, where you will learn about IP addresses, MAC addresses, and how your data is transferring from your computer to the other computer or to the cloud or server or your friend. For that, you have another networking kind of course, but in this course, we will just cover very briefly about this part as well. So anyway, so using this, so CPU is also connected with this input output, which is connected to the internet outside. Through right now with the hard wire, it is a Ethernet connection, or you can connect it with the Wi-Fi, okay, Wi-Fi or Ethernet or any other ways to connect to the internet. Okay, and yes, this is a keyboard, this monitor, and this hard disk, and these are the basic peripherals attached with your computer that makes your computer system. Okay, this is what is computer system. So your computer system is not only this computer, but also when your computer connects to the internet, and you can do so many things there, so that also becomes part of your computer system. Okay, so that's also in this book, not much is covered on that part, but there are other videos that would cover some part of the internet as well, and how the communication happens. So that's about the CPU. Now, when you must be wondering about the cores, right? Cores. So when you have a CPU, how many CPU you think you have? Like how many CPUs on your computer you have? What do you think? Is your computer running on one CPU or multiple CPUs? What do you think? Can somebody say, like, guess or something? Chan Dong Hui, tell me, what do you think on your computer? How many CPUs are there? Is there only one CPU, or you think there could be more CPUs?
More CPUs.
More CPUs? Right, right. So mostly in modern computers, if you are basically having more than one CPU. So on one chip, there could be maybe just one. This is one design where you have here. This is one design where you have two different, you can see that two different chips, but usually in one CPU, you can have like 1, 2 chips, or like this 4 chips, or 8, like 6, 8, or multiple CPUs. Okay, so this is what you say that my computer is a dual core, or okay, so like that you can say your computer is dual core if you have 2 CPUs. You can say quad core if you have 4 CPUs, like that. So can you see your computer and everyone, and you can see this one in here, cores, right? So when you open the task manager, and in the performance section, you can see your CPUs. Can you open your task manager and performance section and see the CPUs? Yeah. You can all see on your computer, right? So there will be cores, right? Cores, and 8 cores. So my computer is 8 core CPU. Okay, 8 cores, something like this. Okay, so 8 processors are running at the same time. Why do I need such a design? Why should we do like this? Why not one CPU do everything? So it's the same concept, like one person doing all the tasks or two-person doing tasks. So there on your computer, you mostly are opening many applications, like sometimes 8-9 applications you are running at the same time, right? So with this kind of architecture, you can use each CPU. You can like the operating system would utilize all these cores to run your application. So 8 application, 8 different CPUs can handle. Okay, like that. So if you have a higher number of CPUs on your computer, like 8 core means good capacity, and you can handle more tasks at the same time. So one CPU will handle your Zoom thing, and the other CPU can handle other application, like that. So all the CPUs can handle different applications. So each CPU again will have their own registers, their own cache. We will talk about it later, and different caches, and their own arithmetic and logic unit. So if you have a 8 core computer, means you can have 8 CPUs running at the same time handling your tasks. Okay, so that is the modern design. So you have not just one CPU. That is what is core means. Okay, core means that you have multiple CPUs running at the same time. Okay, now our computers, as you can see this, in my computer, I have these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. How many you have here? How many do you have? Can you write in the chat? Do you also have 16 or 8 or 4? What is it? How many you have? Write in the chat. You have 8. Somebody said 12. So we have 12, 8, 6, 8, like that. Okay, so now even if your core is, maybe your core is like 2 dual core CPU, but you can have hyper threading. This is because of hyper threading. Okay, this is because of hyper threading. So my computer, even if my computer is 8 core CPU, so there is like 8 cores, there should be only 8 cores showing here, but logically my computer has 16 CPUs. Logically 8 cores, they're physically 8 cores, but each core can handle 2 threads, 2 hyper threads. Okay, so that is called hyper threading. Hyper threading means some CPUs can virtualize, not that every CPU will give this feature to you, not like that. So not that all computers have the hyper threading, but in today's time, most of the computers do have hyper threading. Okay, so some CPUs can virtualize 2 cores for every one physical core. So it has one core like this, it can virtualize 2 cores. What does that mean? Virtualize, what does that mean? Virtualize means that it has some registers, ALU, it has some capacity for doing certain tasks, right? So it can divide that in 2 different sets. Okay, so it can virtually make 2 CPUs out of 1 CPU. Okay, so today's Intel i7 processor is a quad core, plus it can have a hyper threading. So it can show you 16 processors. Okay, 16 processors. So it is virtualizing this resources of this CPU into making two virtual CPUs. Okay, so some dividing the resources kind of thing. That's what is happening in the hyper threading. So virtualizing means that a CPU with only 4 cores can function as if it has 8 cores. This additional virtual CPU cores referred to as separate threads. So basically this mechanism is based on the threading mechanism. That's why it is called the hyper threading, like that. But the idea is that even if your CPUs are only 4 core, you have only 4 cores, your computer can use hyper threading to show 8 cores, like that. So that concept is hyper threading. So even though my computer is 8 cores, I can see 16 CPUs here because of hyper threading. Okay, so I hope that you have understood what hyper threading means. So yeah, so that is hyper threading. And then you might have also heard of GPU, right? GPU. How many of you heard of GPU, right? You already, because I know that everybody, all these young kids like you guys are playing games, right? All the time. You're playing games on your computer, and sometimes you're also playing games on your mobile, right? So you are doing certain tasks, specific tasks, a lot of time, like playing a game is graphics related task, right? It's more of the graphics, right? So there are not so many, probably the tasks that you do in the game is certain kind of task. For example, rendering a high definition, high resolution image. Okay, so when you are rendering a high resolution image, which means you're working on the pixels, and rendering that is like, if it is a high resolution image, you are each pixel, you are doing the same task multiple times. Okay, when you are rendering the image, you are rendering a certain part of your image multiple times. You are rendering, so every time your screen is changing, your image is changing when you are playing the game. So your rendering for the images are very fast. You have to do it very fast, and CPU is not designed to do that kind of task. Okay, so CPU is designed to do arithmetic and logic task. The CPU instruction set, as you can see, add, remove, jump, these kind of instructions. So these kind of instructions CPU can handle fast, because the circuits inside them are designed like that to handle these kind of instructions very fast. But when it comes to rendering the image, there are certain tasks that need to be performed very fast and multiple times. You understand? So to do that kind of task, the GPU was designed. Okay, so GPU is designed to quickly render the high resolution image and video concurrently. Okay, and same with the artificial intelligence. For AI also, there is certain tasks that you execute multiple number of times. For example, in the neural network, if you learn later, if you have interest in AI, you will also see that certain tasks in the neural network, like mapping and backpropagations, are there, that are done like several times. So to do that kind of task multiple times, they have designed, the manufacturers have designed a different kind of CPU, which is called GPU, graphical processing units. So they can process many pieces of data simultaneously, making them useful for machine learning, for video editing, for game applications. So GPUs may be integrated into the computer's CPU or offered as a dedicated hardware unit. So GPU can be together. So is in this image, you can see this is a CPU, and this GPU has two fans, right? You can see that it has two fans because it does processing so fast that it needs, the circuits become hot very quickly. So it needs to cool it more, like you need to cool these GPUs more. That's why you have a fan like this. So this is a GPU design, and it nobody, like we humans are like hungry people, right? We are always, we want something better, something more better, something better than that, like that. So now there is another kind of designs coming, which is also called TPU. Okay, tensor processing unit, TPU. Google is making this tensor processing unit, and this is designed to do certain Google related algorithms. So Google has another a set level of algorithms, right? So they have their own algorithm, and they saw that the normal CPU that is provided by Intel is not processing their algorithms so fast. Okay, they are not able to do that. So they wanted to design their own code, which would specifically process their algorithms very fast. So these days, it is possible that you will see several companies doing the similar kind of thing. So Intel has one CPU. It is a general purpose CPU. Intel CPU we can use on the laptop, on the computers, and all kind of devices. But as the computer engineering grows and becomes mature and more like this, so people may create their own CPU and CPUs to do only their algorithms, so only their instruction set. So their algorithms need certain specific things more number of times, or that kind of things are there, so they can design their own CPU like Google is doing, and it's calling it a TPU. So there is a Google mobile, right? You know, Pixel. So they will use this TPU on their mobile to make it faster. So these kind of things are also happening. It's good to know about it. So in future, because 10 years later, we don't know how our CPUs will look like. Okay, so definitely it will look something very different from what it is right now. Why? Because there is no more capacity for exploring more things in the silicon, like in the transistors. So the sizes cannot go smaller than this, and stuff like that is there. That's why the new designs are going to come in the future. So it is bound to come in the future, the different kind of designs for the CPU. Okay. So that is one important point, that as a future, from the future programmer's perspective, you have to know that, because now you are in engineering for second year, and now you will finish your engineering, go master's, PhD, and then when you go really doing some work in the company, that time the CPU design might be very different, and you may have to work with the different kinds of instruction sets and different kinds of operations. Okay, so to prepare your mind for anything is in the future. So for that reason, this is important to keep in your mind. And the second thing that is important to keep in your mind is the note that I have written here. Okay, the note says that while writing an application, programmers need to exploit these thread level parallelism available. Mostly applications doesn't do that. So what is happening in today's modern applications is that, so for personal computer, it's okay. So you are writing something for the personal computer, for your like, for example, you are writing an application for user to user, like for the commercial use, for like you are writing an app which everybody will install on their computer, on their mobile, and then use that app. For example, for those apps is okay to not use every core, all the cores of your CPU. Okay, because definitely on your computer, not only your app will run, other apps will also run. So there is a requirement that your computer should support all the apps. But in today's time, if you work on the server technology, like for example, you are not working on the user interface of the app, rather you're working on the server side. Okay, so server side, what's happening is every application is divided into kind of microprocessors. Okay, microservices, like small module. So every program is divided into small modules, and all these modules, each modules are deployed on one server. So one module on one server, other module on the other server, like that. So on that server, if you have more CPUs on that server, so one server can have, as you can see, 8, 16, 32 in the server. If you go to the server side, then you will have 32 cores, 64 cores, up to that much. Okay, not just 8 core CPUs. Okay, so in the servers you will have more CPUs. Okay, more CPUs. So if you do not exploit all these cores, and your application is the only application running on the server, okay, only one application. So usually server technologies are like that. So one server, one application only will run. So it will not be like that. This is my server, and I will run Google server here also, IBM server also, Microsoft server also. Not like that. It's not going to be like that. Google means it will only run its own application on that server, right? So that's what I'm saying. And not only that, nowadays small modules in one application, also many modules, and each modules are deployed separately on different virtual machines, okay, on which virtual servers. So it is important that you learn how to utilize all the cores of the computer. So if you are designing on the server side and you just using one core CPU, that's not a good design. That's not good. Okay, so if you are designing one microservice, then you have to, and that you know that it will run on the isolated server, then you have to utilize all the cores. So that is a programmer's perspective, that you cannot leave the other cores useless. Okay, you cannot do that. So you should utilize all the cores, make your program faster for the users. Okay, if you use just one core and you use all the cores, if your design, the code uses every core, then it is better and faster, right? So that is also one thing to remember when you are, and also it depends on you are writing an application for the user for the user mobile or devices like that, or the server. So you have to consider those kind of things, whether you want to use every core on the computer or not. Okay, depending on what type of application you're writing and where it will be deployed, depending on all those things, you will you should exploit your hardwares. Okay, so that's what the other important point is for the future. Okay, so do you understand this slide? Too many information in one slide. Then was I too fast? The problem with this course is if I don't speak fast, we cannot learn enough. There's too many content. Any question? At this point, I will just pause and see if you have any question.
Professor, I have some questions.
Yes.
So what is the real benefit of the hyper-threading? Which means that if we are learning, we are running like a Bitcoin or kind of very high using CPU, those stuffs are really, I think those steps are not needable for hyper-threading. Like, I mean that, yes. So hyper-threading is only using like thread with the low, like gaming only, gaming kind of things, graphic things.
Okay, so the thing about the hyper-threading, as you can see, which application would use it or which application would not use it depends on the definitely the processing requirement of the application. But if your CPU is providing the hyper-threading, it would, for example, as you can see, this is my computer. It does provide hyper-threading. So logically, I have 16 processes. So my computer is capable of running several applications at the same time, because one process can handle one application individually, like isolated from the other application. So it's if I have more processors, I can handle more applications and more tasks. And again, it's not only that 16 processes can only be handled by my computer. It's not right like that. Though at this point, I have 16 processes available due to the hyper-threading. I have 8 CPUs, but each CPU can work as a 2 CPU. So due to the hyper-threading, I have capacity to handle 16. I have 16 processes running at the same time. But how is your application? Does your application need that many CPU or not? It depends on the application. That's what I'm saying to you. So I think what you're saying, the bit mining and stuff like that, they definitely would use a lot of CPU. Okay, so maybe more of a GPU, because they have the same task several times again and again like that. So high capacity of the GPU is required for bit mining and stuff like that. But for depending on your application, how much of this is used depends on the application. At this point, as you can see, it's not used a lot, right? My applications are maybe this core is doing some, this is doing some, this is doing some, but not every core is doing a lot of tasks. Okay, so once you try to load your computer and then check this, try to run a lot of application and then check how your CPUs are getting utilized. You can check all of that. And also the GPU is here. You can also check how much is your GPU getting utilized. So those things you can check on your computer and how much is used and how that application is written. So it's based on basically the application and how it is written. And not only that, also the operating system, how it is handling that application. So my computer has 16 logical processors, but I can run 32, 48, 98, 90 applications at the same time if it can handle. So operating system also does context switching. So if it has only one core CPU, only one CPU, let's say, so one CPU does not mean you will run only one application. It can still run 4 to 5 applications with the context switching. Okay, so I will explain you about that context switching thing later, but it is not limited to this CPU numbers, the applications, and also not that one application will only use one CPU. It can use all these 4 CPUs depending on how your application is written. Okay, so if your application is exploiting the multiple CPU architecture, then it would use all the CPUs. Okay, it can use, one application can use all these CPUs as well, depending on how you have written the application. So it is about that. So am I clear with your question? So I think if you are confused about whether you are playing games, your GPU is used more or the CPU or the hyperthreads are used more, you can check all of that with this and analyze it. Okay. It would depend on application to application, definitely. Okay.
Thank you.
Okay.
Thank you, Professor.
Yeah, so about that. So using all the cores is favorable in server while it's not that efficient for normal work. I think so, right? So when I do programming for myself, so for example, I'm writing some AI algorithm. At that time, I tried to use the algorithm which will use all the cores. Why? Because usually when you are writing an AI algorithm, you will deploy it as a separate on one virtual machine or one container or something like that. And that time you want to use all the resources available to that container or to that virtual machine, because that's the only application that will run on that machine. So why to leave other CPUs for other purposes? Why? Because there is nothing else going to run on that computer. So you can exploit those kind of things for writing your code. Okay, so that's based on my experience, personal experience. Okay, so it's not that people suggest like that, or it's based on my personal experience. You can read about it more as what kind of code you should write. Usually these days the AI algorithms are like they use multiple cores. Okay, so the basic algorithm won't, but as you go advanced, then you will see, oh, this algorithm is going to use all my cores like that. You will find like that. Okay, so that's about this one. Okay, and I will briefly cover this slide. So much to talk. Okay. Okay, now as you see how processors are and how many cores it can have and threads, hyperthreads it can have, so how many applications it can run at the same time. So these are about the processors, but between the hardware and the application, there is another thing which is called operating system, which is in your case maybe Windows or Linux operating system. So there is an operating system also, and it is we need that operating system. And why we need that operating system? Because it manages the hardwares, protects hardwares from unwanted manipulations, and help application developers to manipulate the hardware. So when you are writing the code and you have to access some user interface, like for example, you have to access this monitor or this keyboard or this mouse. For example, you want to do something with the mouse and the keyboard or the camera. Okay, that kind of thing. So these are the hardwares attached to the computer. You cannot directly access these cameras. So usually operating system would provide you with the libraries or something like that, which you can use to access these hardwares. Okay, so operating system is a layer between the hardware and the application programmer. So the computer hardwares are very sophisticated devices, and it is not a good idea to directly access them, though there are softwares they do that, and there are products they do that, but the operating system is a middle level thing which will give you the proper kind of libraries to access these devices, these hardwares. Okay, and then using those APIs you can access them and write your software. So it's a kind of layered view. So this is showing you a layered view of hardware and software. So softwares are usually, when you're writing a software, you will write that software for Windows machine, Linux machine, or like for all the machines. Why you are writing like that? Because of the operating system. Okay. So for example, when you are writing a C program, some functions will access the monitor, and those functions for Windows would be different and for Linux would be different. Okay. So that kind of thing will be there. So operating system is the one which will provide you that layer and those kind of libraries and DLLs which you can use. You can link and use those functions to do certain things with the hardware, not that you can do directly with the hardware. Okay, so you have to use those operating system DLLs or the functions to use those things for your application. So that's the one job of the operating system, but that's not the only job of the operating system. Operating system also help the processor. So the processes. So what happens, as I told you in the previous example also, that if I have only one core CPU, let's say one core CPU, then there would be many applications running on the CPU. How would the CPU manage it? Okay, so CPU has a set of registers, ALU, and how is the CPU going to manage that kind of task? So I am running two tasks at the same time. How is it managing? So operating system also helps do that. Okay, so what does operating system do is you write one code. So you're running that code, and there is another code which is running on the same CPU. Then operating system is doing this kind of thing. So one processor. So it gives you a feel that only your application is running on this computer. No other application is running on this computer. It gives you that feel, right? So that task is also done by the operating system. Okay, so usually your program will run as a process. As you can see in here, there are multiple processes running. You can also see how many processes are running here, like process 238 process at this time. My computer is running, right? And how come these many processes is running? I have only 16 processors. So it is running, but still it is running so many processes. Okay, so that is the task of the operating system to do the context switching between the processes. So one time my CPU is running one process, and then next time clock it is running another process. So that is a kind of context switching. Okay, context switching task. So context switching happens at several kind of system calls. The context switching can happen. For example, right now my computer is running only this one in the front, right? This presentation, this presentation. Oh, sorry. So this presentation file. Okay, my mouse was on my computer, so I think I missed to explain this. Miyane. Now ego chigam salmia kago inande, but my slide was here. I'm so sorry. Do I have to explain again? Did you guys see this slide on the monitor? No, right? Okay. So I'm talking about this slide. I confused a lot of you. I'm so sorry about that. So I first talked about the operating system. Okay, this part of it, okay. Getting it now, right? What I explained. Neo. So I explained to you there is a hardware, and then there is an application. In between there is an operating system. Okay, so operating system provide you a middle layer between the hardware and the software. So operating system is a set of DLLs and libraries that you can, in the case of a Windows, it is a DLL. Okay, so using you link those DLLs and use those APIs to deal with these hardwares. Okay, so it provides you the layer, plus operating system also provides you with the view of this kind of thing. So as I told you here, you can see that in my computer has only 16 processes running, but in here it is 16 cores, but this computer is handling how many processes? 238 processes at this time. So how it is doing that? It is doing that through context switching. So one processor, this one processor may be handling 10, 15 processes at the same time. Okay, so it does that with the help of the context switching. So what is context switching? We will learn more about context switching in the chapter 8, but to briefly explain you what is context switching is that when there is some kind of right now the course are executing, for example, this particular Zoom and let's say this particular presentation file, and I click and I want to close this application. So let's say I just stop sharing like this. Okay, this kind of thing. So this is kind of interrupt. Okay, some kind of interrupt is happening. So okay, again I will share. So this is a kind of interrupt. So operating system would do the context switching with some kind of interrupt. Those interrupts can be from the click of a button, like closing something, opening something, or from the keyboard, or some kind of IO interrupt, or from the code itself, there could be an interrupt. Okay, the code itself will do some kind of things to do the context switching. So there could be interrupts. Okay, interrupts. And so for example, this particular image will explain you that. So you have two processes running on the same CPU. Okay, two processes are running. Then how does it do the context switching? So there will be, let's say there is a read operation. Okay, so where you have to go and read something, some kind of read operation, which is a kind of interrupt, as I told you, like a click or from the mouse, or there could be some system calls as well. So in this case, there is a read system call of some type. So process 1 was running and suddenly there is another interrupt coming. So operating system would switch. Okay, so this is a user mode. It was running a user mode and it switches to the kernel mode. This is called context switching, and the processor is now processing process B. So when I did a stop share, for example, this kind of thing, that time my monitor was dedicated for this particular monitor, and when I stop sharing means again I'm going to the next monitor. So that is a kind of interrupt. So if that interrupt happens, that interrupt is handled by operating system. So operating system, that call goes to the operating system. Operating system now gives the processor to the next process that is on the focus, for example. Okay, so it is now processing the next process. So process B, which is my screen, Zoom screen, where all of you are shown, right? So the other screen is being processed. And then another interrupt happened, I go back. Okay, so it could be a disk interrupt like that. So this interrupt is handled by the operating system, and then it will do the context switching. So this process, then this process, and then this process. So one core is running multiple processes based on the context switching. So one core can run multiple processes. So you leave this process on this state. So when we read the chapter 8, we will see in detail how exactly the context switching happens and how the computer stores this state of this process. So the process can have multiple states, like runnable, running, that kind of states. So there are many states for the process. And when you do the context switching, this state has to be saved. So in the CPU, there are some registers, right? Registers that are storing some data about this process. Okay, this process needs these temporary data, the registers are storing them and working on them, right? And there is a context switching. So all these registers have to be swiped out and then new process is coming. So this process data will be on the registers, right? So how this is working, and so how this gets swiped out and then come back. When we come back to this process again, all those data again will be loaded in the registers. So that kind of, so there is a lot going when we do the context switching, when the operating system does the context switching. So there is a mechanism to do the context switching. We will learn more about that in chapter 8 in very detail. So basically, that is the task of the operating system as well. We call that kernel, okay, kernel. So the process in the operating system, let's read this paragraph because these are from the book. Okay, so what is process? A process is an operating system's abstraction for running a program. A single CPU can appear to execute multiple processes concurrently by having processors switch among them. How they do that? Using context switching. Okay, OS kernel, operating system, has a special program called kernel. Okay, kernel is a special program that is doing the context switching. So in your first programming assignments, like your lab, you will listen to kernel. Okay, you will have a kernel lab. So when you have a kernel lab, it is basically this kernel. Okay, so you will learn about the kernel. Okay, so kernel does the context switching. So context switching is done with the help of operating system kernel. Now in the Linux, you have you are going to use, I think for your exercises, you are going to use the Linux machine, and we have a GNU and Linux, two kind of organizations were there in past. GNU had a operating system, okay, but its kernel was not so good. The kernel that's doing the context switching, that part of the operating system, that's like a core of the operating system. You can say it is a heart of the operating system. That was not very good, well written, okay. Then there came the Linux kernel. Okay, so Linux kernel was very good, very efficient, and then GNU adopted the Linux kernel. Okay, so it had all the IO processors and other operating system has too many tasks, other tasks as well, not only the kernel. Kernel is one of the tasks, but operating system is also having other tasks. Dealing with the input-output devices and other tasks are also there, plus kernel. So kernel is the very important part of the operating system. So what GNU did was that it used the Linux kernel. So at this point also we have a confusion whether we should call Linux a Linux or we should call it a GNU. What should we call it? Like that. That confusion is still there, but actually GNU was a full operating system, but its kernel was not good. So they used the Linux kernel, and now they have the full Linux. So sometimes people call it a Linux, sometimes they call it a GNU, like that. No? Unix or Linux. So this kind of confusion is still there. Why? Because Unix means everything was there, but the kernel was not so strong. So Linux, another operating system, its kernel was strong, it was free software, so it was possible to combine that kernel into the GNU system, okay, operating system, and then it is a Unix system. So you call it Unix, sometimes you call it Linux. So that confusion is still on. Should I call it Unix? Should I call it Linux? What should I call? Okay, its confusion is because of this. Okay, because of this. So I just wanted to tell you about this story, why this confusion is there. And there are, these kernels have different distributors are there, right? So like Red Hat or Fedora or Ubuntu, maybe in your kernel experiments, you are going to use Ubuntu distribution. So that is a kind of distribution for this. So because Unix is free and it is developed by the Free Software Foundation, so different organizations decided to provide the distribution for this and support for this. Basically, if something need to be improved on the Unix, so your Ubuntu is an organization that's going to improve it and provide you the new version of it or something like that. So there are another distributors as well, like Fedora, Red Hat, and another kind of distributors as well. Okay, so these are just the companies. Okay, companies. So when you see Ubuntu Linux, Ubuntu Unix, Red Hat Unix, what is the difference? They are nothing. Same inside, the kernel is same, just the distribution is done by these companies. So that's it for today's class. We have no time for questions. Keep your question for the next class. Okay, and we'll see you next time. Okay, see you guys. Bye. If you have any questions, keep it in your mind, and I will upload this video on Gel so you can go through it again. Okay, bye-bye. Bye.
Thank you.
Thank you, Professor.
Thank you. Bye-bye.